DNS. In the landscape of modern computer networks, a host is any device that can send or receive data across the wire. However, some hosts are more powerful than others. When a host is configured to provide a specific resource or a critical function to other devices on the network, it takes on a specialized server role. One of the most foundational of these roles is the Domain Name System, or DNS server. Without this specific host, the internet as we know it would be impossible for humans to navigate. To truly understand the power and complexity of the DNS role, we must examine its internal hierarchy, the specific record types it manages, and the multi-step process it follows to resolve a query. The architecture of the DNS server role. A DNS server functions as a globally distributed database. Its primary job is to translate human-readable names, like Google.com or MinuteHow.com, into machine-readable numeric IP addresses, like 8.8.8.8. But no single host contains every single name in the world. Instead, the DNS role is divided into a strict hierarchy. At the very top are the root name servers. These are the ultimate authorities. They do not know every IP address, but they know exactly who is in charge of the top-level domains, like .com, .org, or .net. Below the root are the TLD servers. These hosts manage all the domains within their specific extension. For example, the .com TLD server knows the location of the next level down, the authoritative name server. The authoritative name server is the final destination. This is the host that actually holds the master records for a specific website. When you update the settings for your own domains, you are changing the information stored on an authoritative name server. The resolution process, recursive versus iterative. When a user's computer, known as a DNS client or resolver, needs to find a website, the DNS host follows a specific process to find the answer. This is where we see the difference between recursive and iterative queries. When you type a web address into your browser, your computer sends a recursive query to your local DNS server, usually provided by your internet service provider. A recursive query basically says, "I need the IP address for this name, and I am going to wait here until you find it for me." The local server takes on the full responsibility of finding the answer. The local server then performs a series of iterative queries. It asks the root server, "Where is .com?" The root server replies, "I don't know the exact IP, but here is the location of the .com TLD server." The local server then asks the TLD server, "Where is MinuteHow.com?" The TLD server replies, "Here is the location of the authoritative server for that domain." Finally, the local server asks the authoritative server for the record, gets the IP address, and passes it back to your computer. Managing the database, common record types. The DNS server role is defined by the types of records it manages. As an administrator, you must be intimately familiar with these 5 core types. First is the A record. This is the most common record, used to map a domain name to a standard 32-bit IP version 4 address. Second is the Quad A record, or AAAA. This performs the exact same task, but for the much larger 128-bit IP version 6 addresses, as the world transitions away from version 4. The Quad A record is becoming a critical security and routing standard. Third is the CNAME, or canonical name. This is an alias record. It allows you to point one name to another name. For example, you can point www.domain.com to your primary server1.domain.com record. This makes management much easier because if the server's IP address changes, you only have to update it in one single place. Fourth is the MX record, or mail exchanger. This tells the internet where to send your email. It points to a mail server and uses a priority or preference value. If you have multiple mail servers, the sending server will always try the one with the lowest priority number first, ensuring your email has a backup path if the primary server fails. Fifth is the TXT record. This is a versatile text container. While it was originally for notes, it is now the primary tool for email security. It holds SBF records to authorize senders and DKIM public keys to verify digital signatures, preventing hackers from spoofing your domain. Caching and time to live, TTL. To prevent the internet from being overwhelmed by millions of repeated queries, DNS hosts use a process called caching. When a server finds an answer for a domain, it keeps a copy of that record in its local memory. If another user asks for the same website, 5 minutes later, the server can provide the answer instantly from its cache without having to go through the entire resolution process again. However, information on the internet changes. To ensure that servers don't keep old, incorrect data forever, every DNS record has a time to live, or TTL value. This is a timer, measured in seconds, that tells other servers how long they are allowed to keep the record in their cache. Once the timer hits 0, the server must discard the cached copy and perform a fresh lookup the next time it is asked. The security aspect, DNS attacks and protection. Because every single connection starts with a DNS lookup, this host role is a primary target for cyber attacks. One of the most dangerous is DNS poisoning. This is where an attacker injects a fake record into a server's cache. If an attacker can replace a legitimate bank IP address with the IP address of their own malicious server, they can silently redirect thousands of users to a fraudulent website to steal their credentials. To combat this, the industry is moving toward DNSSEC, or DNS security extensions. This adds digital signatures to DNS records, allowing a server to verify that the information it is receiving is legitimate and has not been tampered with by a hacker. By mastering the hierarchy, the resolution process, and the critical record types, you will understand why the DNS server role is the brain of the network, and how to protect it from the threats of the modern digital landscape.